of the battery pack, ensuring that your EV operates intelligently, safely, and efficiently. Today, we'll explore the intricacies of BMS technology from its fundamental principles to real world applications and gain insights into its manufacturing and testing processes. So, let me introduce our experts for today. We are honored to have with us two distinguished speakers in the field of EV technology, Mr. Ashwani Pandey and Mr. Siddharth Wadhwani. So, coming to Mr. Ashwani, he has over 7 years of experience in the clean energy domain. Ashwani holds a master's degree in material science from IIT Bhubaneswar. He is a dedicated researcher and entrepreneur, having worked on various research projects, including those for DRDO. Ashwani specializes in silicon-based battery technology, focusing on developing materials and technologies for advanced lithium cells and battery packs. Currently, he serves as the managing director of Cellar PowerTech, leading efforts in indigenizing lithium-ion cell technology with advanced silicon anodes. Coming to Mr. Siddharth, he is a seasoned lithium battery technology consultant and the founder of Fuel Out Technologies, bringing over 8 years of hands on experience in the lithium battery domain. He holds a Bachelor of Technology degree in Electronics and Communication Engineering and has conducted research at the Conn Center of Renewable Energy Research, University of Louisville, Kentucky, USA. Siddharth has collaborated with over 10 clients driving innovation in areas such as product development, quality control, lithium battery assembly lineup, and business strategy consulting. Under his leadership, Fuel Out Technologies empowers energy storage businesses with expert driven solutions tailored to the evolving energy landscape. So please join me in welcoming Ashwani and Siddharth to today's session. So, coming to what we have lined up for you today, we will go through the fundamentals of BMS, understanding why BMS is termed the brain of EVs, exploring its core functions, discussing the different types of BMS that are there. Then we go on to the challenges and innovations in BMS, identifying key engineering challenges, delving into thermal management, safety, state of health, and state of charge estimation. And we will also explore a few emerging trends. Then we will have a virtual walkthrough of the BMS manufacturing and testing area at Sela PowerTech, where we will go through a real-time demonstration of BMS components, integration steps, and testing tools, which will have expert insights from the Sela PowerTech team. Then we'll also highlight a few roles and skills in demand. We'll go through a few career opportunities in this space, and then we'll throw the floor open for your questions. So we aim to make this session engaging, informative, and rich with practical insights. So without further ado, let's delve into the session. Ashwani and Siddharth, the floor is yours.
Thank you, Tanjeev. Thanks a lot. Uh, I can hear a lot of echo going on. Can you mute? Yeah, yeah. So thanks a lot for the lovely introduction. And as Tanjeev actually pointed out, many intricacies related to BMS, starting from BMS functions, SOC monitoring, SOH monitoring, innovation, and all. And I would like to make it clear that BMS is a very very deep subject. It's not possible to cover this width of the subject in less than 30 minutes or so, but we will try to we'll try to briefly cover the basic aspects of BMS, what BMS does, and what are the future directions that are there people are trying to solve in terms of challenges that are there inside a BMS technology domain. So in first session, I will go through the basics of BMS functions, and then I will hand over to Mr. Siddharth. He will talk more about the hardwares of BMS, and then he will shed some light on SOC SOH monitoring and what are the integration of AI and ML techniques in SOC and SOH monitorings. So let me share my screen. Uh, okay, it's visible.
Yes.
Okay. So I will be basically talking about the introductory part of battery management system and why do we call it the heart of modern energy storage devices. And about me, already Tanjeev has explained. I'm co-founder and CEO of Solar Power Tech. And in addition to that, I'm also associated with REP IIT Bhubaneswar, basically for electric vehicle training programs. On the right hand side, you can see a small, PCB board I have presented here. And this PCB board is actually from Tesla Model S. They are using modular configuration of BMS. And with this small PCB circuit, they are actually ensuring the long life of their battery pack. They are ensuring the smooth communication between chargers, between the vehicle and the battery packs. They are doing a lot of data acquisition and monitoring of state of charge and everything. So this is the actual circuit through which they do current monitoring, voltage monitoring, temperature monitoring and everything. And finally, with the help of those data and communication protocols, they are ensuring the long life and smooth operation, safe operation of their vehicles. And before I go into some deeper aspects of battery management system, it's really necessary to understand the fundamental of lithium ion battery operation. And of course, these battery management systems are applicable to any batteries irrespective of chemistries. So BMS are applicable to lead acid batteries, nickel metal hydride batteries, even in the different variants of lithium ion battery chemistry, as well as for upcoming sodium ion chemistry as well. But since we are dealing into the domain of electric vehicle technology, and we all know that most of the vehicles are nowadays most of the vehicles are coming with lithium ion batteries, and of course owning to its high energy density and good charge discharge capability, uh, approximate around 8 to 10 years of cycle life in the vehicle, and cost is also going little bit steep coming down, and we are expecting the cost to be approximately 60 to $70 per kilowatt hour in coming 2030. And that is why my major entire presentation will revolve around the management of lithium ion battery. So we will not going to cover other battery chemistries here in this particular webinar. So here I am trying to showcase the working mechanism of lithium ion battery. In the first dynamic GIF presentation, you can see we have a working schematic block, and on the left side we have anode, which is made of graphite material. On the right hand side we have a cathode, which is any cathode, like you can use LFP, LCO, or combination of NMC or so. Uh, but here I'm trying to represent NMC working mechanism. Okay, so while charge condition, a lot of lithiums are stored inside a graphite material, and the moment you connect certain load across these batteries, the batteries start discharging. And you can see that these red ions are there, which are floating from left side to right side and slowly passing through the separator and going inside the cathode material. So this is what happening during discharge reaction. So the lithium ions travels from left to right. At the same time, they are releasing certain electrons, which is going across the load. And when this phenomena is happening, you can see in the small inset subset plot here, the discharging is taking place and SOC of the battery is going down. On the right hand side, I have tried to plot plot this discharge feature of lithium ion battery in terms of capacity versus voltage plot that we do during discharge testing of the cells. And you can see, okay, let me take when. Yeah, you can see while when the battery was fully charged, its voltage was around 4.2 volt. So since it is an MC battery, so nominal voltage is around 3.7 volt, and usually manufacturer defines the charging and discharging cutoff voltage. So for in this case, it is around 4.2 volt in upper limit in charging and 2.5 volt during discharging. The moment the battery starts discharging, the voltage is slowly going down, going through across various voltage plateaus, and finally it is coming around 2.5 volt where the entire capacity has been obtained from the cell. So this particular cell which was tested, it had around 2.7 ah of capacity. It's a cylindrical 18650 cell only. While charging, you can see the voltage slowly increasing from 2.5 volt, again going towards upper voltage plateau. Different plateaus are there, and finally reaching to 4.2 volt. And we have used CCCV voltage profile for charging this cell. And that's why you are seeing a constant voltage plateau at 4.25 volt. Now, the reason I have included this charge discharge curve is that a very core observation is there from this charge discharge profile is that we are trying to stop the discharge at 2.5 volt, and we are trying to stop the charge at 4.2 volt. And there is a reason behind doing that, and the reason actually comes across the working mechanism of lithium ion battery. So what happens when you try to deep discharge the cell? You see these red ions are already while discharging already gone from anode to cathode. Now no lithium is there inside anode material. If you further try to discharge this particular battery, what will happen? There is a layer called solid electrolyte interface. It will start crumbling. Uh, also certain low potential can generate electrolyte dissociation as well, and copper dissolution can also occur. Now these phenomena actually degrade the battery a lot, so you will compromise on the cycle life of the battery. On another hand, if you try to overcharge your battery, what will happen? More and more lithium will go inside anode material, and of course there is a limit for this particular lithium to go inside this anode. When the entire spaces where lithium can go inside it has been fulfilled, and you keep on charging the battery, what will happen? These lithium will start depositing over the surface of anode material, and that's how you depositing dendrite lithium formation, and slowly it will grow. It will pierce the separator, and finally it will contact the cathode, and internal short circuit can occur. So from this phenomena, you can appreciate the fact that there is a certain window of these lithium ion battery operation. So that window is there in terms of upper charging cutoff, lower discharging cutoff. Of course, there is a limitation in terms of how much current you can pull out from the system, and or how much current you can put while charging the lithium ion battery, that is called C rate capability of the battery. And in addition to that, there is also a limit in terms of temperature window for a smooth operation of this battery. So usually lithium ion battery do not perform well below 15 degrees Celsius or above 45 or 50 degrees Celsius. So we need to club, to operate the lithium ion battery in those safe and operational limit of voltage, temperature, and current. And with having said that, now we can appreciate that, of course, there is a need for some external intervention which can actually ensure that the battery is being operated inside a safer limit. And that's exactly BMS does. And that's why BMS is necessary. And of course, there is a limitation on the technology side. But if you look at another aspect in terms of what the customers are asking from these EVs or these electric EV batteries, they are looking for more and more energy density from their battery pack. So what OEMs are doing, they are trying to pack more and more material inside a limited volume. So these safe criteria becomes more and more stringent. customers want their battery to be charged in less than 10 minutes or maybe 20 minutes or so. And we understood that there is a certain C rate, limitation is there. And if you try to pump more charge, there might be a problem of thermal runaway or safety issues. So we need to arrange certain electronic management system who can control these phenomena in a optimized manner. So I will emphasize on the fact, what I already talked about, that there is an impact of C rate capability or charging discharging rate capability on the cycle life of the cell. And this graph actually represents the phenomena of cycle life fading with respect to higher C rate operation. So you can see the blue line is for 1C charging and discharging, and in case of blue line, we are achieving approximately 500 cycles of operation from the lithium ion cell. While when we try to do this operation at 2C charge and 2C discharge, we are compromising on the cycle life fading. And further, at 3C charge discharge rate, the cycle life is further degrading. Okay, so this is basically try to understand this with an example that let's say you have electric vehicle which is not designed to handle 3C charge or discharge rate, but on the way while driving you came across certain charger which can some kind of fast charger is there which can put lot of current in a small duration of time. So you plugged in your vehicle with this 3C charger. So what will happen? It will compromise your uh, health of the battery. So at this point you need certain mechanism through which your battery can communicate with the charger, and it can tell the charger, no, I am not designed for this particular current rate, I won't take this much of charge. So either you reduce the current or I will go to another charging station or so. And this communication will be done by the battery management system. Now this rate capability, when combined with the higher temperature or lower temperature phenomena, this cycle life fading further increases by twofold ratio. And you can see that there is an optimum temperature range across which lithium ion battery performs well. So for example, here in between 15 degrees Celsius to around 45 degrees Celsius, at 1C you can easily achieve around 1200 cycles of operation. 3C you can achieve at maybe 760 or 780 cycles of operation. But the moment you move from the safe operational range to 60 degrees Celsius, you see slowly the cycle fading gap is increased. Okay. So high temperature in combination with high rate capability will further downgrade your battery life, and it can cause various safety problem as well, causing to thermal runaway phenomenon. So these phenomena need to be gauged properly, and based on those data acquisition, certain electronic mechanism has to be there which restricts these phenomena. One more example is there in terms of higher voltage charging capability, and you can see I try to compare basically the cycle life of the cell with respect to the cutoff charging voltage. So we had 4.2 volt, we had upper cutoff of 4.25, 4.3, and 4.35. And you can clearly see in the graph that when we try to operate at upper cutoff of 4.35 volt, how much cycle life has been compromised in this lithium ion battery. Okay. So that is why it is really necessary to properly monitor, very precisely monitor the voltage of the cell during operation, and based on those monitoring and set parameters, BMS has to take certain decision to ensure that the battery goes through a longer cycle life in a safer manner. On the right hand side, again, a lot of data I am trying to present here because it will make more sense in terms of operational features or operational parameters, how they impact the battery life. So on the right hand side, we have a DOD effect. DOD is basically depth of discharge of the battery. So how much energy you are actually utilizing from the overall energy inside the cell. So that is called depth of discharge. And you can see the impact of depth of discharge on the cycle life of the cell. So basically, you see this black curve is basically for DOD from 25% to 100% state of charge we are trying to operate. When you try to reduce or squeeze the DOD, of course, we are increasing the cycle life, and which is visible from this particular plot here. So this battery is being operated in a very small SOC range, that is 75 to 65% SOC level. So that's how this DOD also impact the cycle life and the battery performance inside electric vehicles. And these all DOD monitoring, DOD parameter setting, these all things can be done with the help of battery management system inside a vehicle. Now, these were the problems at cell level, but in the system level, the problem is much more complex, because we know that most of the battery packs are designed to have, in case of two wheeler and three wheeler, we have 48 volt to 60 or maybe 72-volt powertrain, while in case of four wheeler, the voltage ranges in between 240 to maybe 400 volt, or in some cases it can go beyond 600 volt as well. And we know that individual cell has a very small voltage of 3.7 volt. So to meet that voltage demand and capacity demand, we need to pack number of cells in series and parallel condition, and that's how we make a battery pack, making so it can occur through modular arrangement or directly making in a battery pack such as cell to pack configuration. And when you make this battery pack, of course, to increase the voltage, we will add the cells in series to increase the range or AH capacity in parallel. And that's how, with a combination of series and parallel configuration, we meet the power capability requirement and the energy capability requirement of the vehicle. Now, think about this. So, this is again, I'm trying to showcase a Tesla S battery pack here. So it is designed to operate at 400 volt, and this is 90 kilowatt hour battery pack. And you can see that it is a combination of different modules. So around one, two, three, around 16 modules are there, which are assembled together to make the battery pack. And inside a single module, so this is the single module, this one is single module. Inside a single module, we have 440 number of cells. And if you combine the overall cell that goes inside a battery pack, it is more than 7,000 cells connected together. So this is the case for a particular Tesla S model, where of course it's a older version of Tesla S, where they were using around 18650 cells with a voltage of 3.7 volt and 3 Ah capacity. Now, just imagine that 7,000 cells need to be monitored in terms of voltage, to ensure that no overcharge, no over discharge is happening. At the same time, temperature variation across the entire battery pack has to be monitored. At the same time, current has to be monitored. A lot of data acquisition has to be done on the cell level or maybe at module level. So SOC, SOH estimation is needed, and the entire battery pack has to communicate on two front, on the charger side as well as on the vehicle side. So just think about the extent of problem in terms of electronic management of these individual 700 cells, ensuring the smooth operation of these seven not 700, sorry, 7,000 cells, and providing a life of maybe 8 to 10 years. Okay, and that is the core challenge. So I have already listed out the core challenges that we face in terms of these maintaining or safe operation of these battery packs, how to monitor and control the charge and discharge voltage. And in addition to that, a very common phenomena happens inside a battery pack while operation, which is called cell imbalancing. So at the same time, you have to go for cell balancing also. You have to maintain the optimum temperature. You have to do SOC, SOH estimation, and communication with the vehicle and charge. So that's exactly, these are the challenges which is being solved with the help of battery management system. So BMS actually does many tasks. I usually try to bifurcate it into three major tasks. So one is the core task, which is the for the BMS. The core task is, of course, monitoring the cell voltage, doing the cell balancing, SOC, state of charge, and SOH estimation. A lot of communication take place across the battery pack, diagnostic, sending the signal to ECUs, and basically SOC and SOH estimation is basically a mathematical calculation, algorithm based calculation. And while real operation of the vehicle, we come across different parameters which have direct impact on these SOC SOH estimation techniques. So a lot of adaptation and compensation also takes place inside the battery management system. And at the same time, it also communicates with the TMS thing. So it does not directly manages the thermal management part of the battery pack, but it is responsible for sending the signal to switch on the thermal management or switch off the thermal management at a particular time frame with respect to the heat generated, calculation of heat generated, or current time frame. Other core function of the BMS is communicating with the charger. So it constantly when the charger is plugged in with the battery pack, it communicates with the charger, it sends the signal about the state of charge of the battery pack, and it tells the right amount of current that is needed to charge the battery pack. It also communicates with the regeneration controller of the motor when doing the regeneration braking energy harvesting. On the vehicle side, it tries to communicate with the motor controller and vehicle management system. So let's say a kind of range optimization, or you have a certain a battery capacity remaining with you, and you want to cover a certain amount of distance. So what it will do, it will try to limit the energy, it will try to limit the acceleration or current that is coming from the vehicle, and that's how it will ensure that you get your range that is required. And also it does a lot of power limitation strategy as well. If you look at the BMS topology that is being practiced inside the industry, there are four core mechanisms through which BMS are integrated with the battery packs. First being the centralized BMS, second is decentralized BMS, third is modular BMS, and fourth is, of course, the combination of all these three, maybe centralized combined with decentralized, or maybe modular combined with centralized, which is called hybrid BMS arrangement. So we'll briefly touch upon the different topology here. In case of centralized BMS, what we do, we try to monitor, we try to control or communicate with all the cells individually. So in this example, you can see we had around 80 cells, and here one central master control unit, central BMS is there, which is trying to communicate with all the 80 cells. So I'm having voltage monitoring of all the 80 cells. I'm having all the SOC, SOH. I don't know. So maybe you can do SOC, SOH level calculation on the pack level, as well as on the cell level is also possible. So all the communication and monitoring happens across the cells. While in case of distributed BMS, we do monitoring and communication at cell level. For example, here, if you look at the insert picture here, there is a BMS connected with individual cell here. Okay, so we have 80 cells. So we will be having 80 pieces or circuit board which will be doing voltage monitoring or whatever monitoring is required on all the cell levels. And finally, it will be communicating with the central communication protocol with the vehicle, right? So that's how distributed BMS work. Uh, for example, Tesla has actually uses in earlier model. I do not know in the newer models, but in earlier model it used centralized BMS mechanism. While Nissan Leaf, I think, use distributed BMS modules. Now another topology is modular BMS. We already saw that we have around 7,000 cells connected to make the battery packs. So it's easier to make the battery pack in a modular configuration instead of making the entire battery pack, and that's why we had around 16 modules there, right? So what we do in modular BMS, we have individual modules, and for each individual modules we will be having individual BMS connected with it. For example, here we have 5 slave BMS unit which is connected with the one master BMS unit. Now these individual slave units are actually controlling 16, around 16 cells. Okay, and that's how 16 multiplied by 5, it will be 80 cells. So each slave unit is trying to communicate and monitor with 16 cells, a single module, and then it is sending all the signals to master control unit, which is communicating or sending signal to vehicle management system, or doing the last job. So this is how the BMS topology work, and this modular configuration is very popular today. And I think BMW i3 model actually uses this modular BMS. Also, these centralized BMS are very popular in small battery packs like two-wheeler and three-wheeler battery packs, where the cell number is very limited. For example, three-wheeler e-rickshaw battery of maybe 60 volt or 100 Ah or 200 Ah, it has approximately 16 to 20 cells. And usually you will get a centralized BMS in the market having 21 series configuration. So those centralized BMS, you can directly connect with all the cells all together, and you can utilize the BMS feature there. So that's all from my side. I think I took little bit more time, but now I would like to invite Mr. Siddharth to take it from here and shed some light on SOC algorithms and few aspects on the hardware of BMS as well. And we can take the questions in end of the session when we have all the walkthrough, or the live walkthrough company testing and all.
Yeah, hello everyone. Thank you, Ashwini, for giving me the chance to speak, and thank you, Tanji, for the detailed introduction that you gave about me and my company. So I guess a lot of points have been covered by Mr. Ashwani on how why BMS actually is important, and what are its what complications does lithium ion have, for which the BMS is required. And there has been a lot of, I mean, everyone throws a lot of light on what kind of research is going on the cell level, but there's very limited talk about what kind of research is going on the BMS level, where I feel that BMS holds a very important part, when we are making the complete battery pack. So I'll just start with my presentation, and I'll try to explain what are the key challenges while you're making the BMS. How do you consider, like, what kind of SOC algorithms you want to choose, what kind of balancing you want to choose, what kind of ICs and MOSFETs you want to choose for your BMS, and then how to create a product, and then I'll give you a quick walkthrough of how the BMS testing happens and how it is integrated with the battery. Just give me a second for sharing the screen. I hope my screen is visible. Yeah. So I'll first guide you through what are the basic engineering challenges that the development or the BMS engineer faces while designing a particular BMS for their application. So starting with the first and most important point, which Mr. Ashmi also shared and discussed, what SOC estimation. Because SOC estimation, when you see the graph of a LFP battery or an MC battery, it is not completely linear. Okay, it is linear for most of the phases. If I talk about LFP chemistry, so you might have observed in the graph shared by Mr. Ashwani that it is linear through the middle phase, but it is non-linear through the starting and the ending phase. So that is where the play happens, because you will not be able to predict the actual SOC at the starting phase and at the ending phase. So there are a lot of algorithms available for SOC estimations, like Kalman filter and other kinds of SOC driven models. So you will have to choose based upon how. First, you have to understand what is the curve for your battery pack, what is the voltage versus capacity curve that is present for your battery pack, and then accordingly select what kind of SOC calculation method that you need. So, like in Kalman filter, Kalman filter combines basically Coulomb counting and voltage-based SOC method. In Coulomb counting, what happens is there's a Coulomb counter in between the battery pack, which measures the current which is carrying through the battery pack with respect to time, and that is how it calculates. Okay, this is the capacity left, and it automatically gives the SOC value. When we talk about voltage-based SOC, it is not accurate, but it is depends upon the voltage. Let's say my battery voltage is at 3.2, so the worth will determine, okay, at this particular voltage, this will be the actual capacity left based on the curves of the battery pack that are available, the charge and discharge curves that are available, and automatically predict the SOC of the battery pack. And there are a lot of things which are coming new into the picture. Is more they are more dependent on the data driven model. So when I talk about the data-driven model, so there will be since the battery is something which goes into different terrains. I mean, if it is mounted on electric vehicle, let's say you are taking your car to Himachal Pradesh, or you're taking your car to areas where, let's say, rural areas where roads are not even. Okay, so the capacity delivered of the battery pack will change, obviously, because of the temperature conditions, because of the road conditions, because of the vibration conditions. Okay, so a lot of development are being done in that aspect, where people are trying to get the data sets of different terrains and then analyze, okay, what is the actual SOC that is being generated at different voltage level in a particular terrain or environmental condition. So this is one basic challenge that everyone faces on how to determine the exact SOC. Apart from that, the other challenge that people face is SOH monitoring. So SOC is based on the total capacity that you are able to deliver or get from the battery pack. SOH is basically over the time how much capacity is degrading over the time, which is again a challenge, because when you see lithium battery pack, there is if you see the battery pack, so the cycle life of those cells is very very high. I mean, in electric chemistry, basically nowadays, cells are coming with cycle life of, let's say, 10,000 or 12,000 and things like these. So in those areas, like, how will you decide, like, after every cycle, or after, let's say, every 200 or 300 cycles, what is the SOH left? So that is again a different challenge, where, because you need to have an idea on SOH degradation over time to be able to give the exact lifetime, or life duration of the battery pack to your clients, or to your customers. So that is also done in a different way, where the SOH can be directly related to the resistance or the impedance of the battery pack. As soon as let's say the impedance is increasing, that means the capacity is getting lost, because if you see the heat generation formula or the losses formula, it is directly proportional to resistance, right? So if the resistance is increasing, that means the capacity is getting lost, or in form of heat, or other factors, and that will ultimately affect the state of health of your battery pack. And then again, you can also have a cyclic aging models, where we do accelerated rate calorimetry test, where we assume that, okay, if in a, let's say, we cycle the battery pack at 2C at a particular temperature, and then we assume using those data sets, okay, if this battery is performing at extreme temperature and extreme condition in a particular way, so this is how it will perform in this particular condition, in a way to calculate the SOH of the battery pack. The other important parameter that needs to be considered while designing a BMS is cell balancing technique. Now, when we talk about cell balancing technique, there are two types of techniques available. One is active balancing, one is passive balancing. Passive balancing works in a way where, let's say, you have 16 cells in series. There will be bleed resistors connected to all the series, all the strings. And if a particular cell goes above a particular voltage, delta limit between the cells increases, delta voltage limit between the cells increases. Let's say one cell is at 3.325 volt, one cell is at 3. Let's say 250 volt. So we have a delta of, let's say, 100 millivolt or something like that. So in passive balancing, how it happens is that particular cell which is at higher potential bleed its energy out using the bleed resistors which are present in the BMS circuit, and then tries to bring their voltage to a particular limit. Whereas in active balancing, it is slightly different. In active balancing, transfer of energy happens between the cells. There is nothing, no resistor or no dissipating components present. It is just transferring energy from one cell, one which is at a higher potential, to a lower potential cell. So again, both of these techniques have their pros and cons. If you are using active balancing, you are consuming more energy, because you are actually transferring energy from one cell to the other cell. When you're using passive balancing, and obviously active balancing happens at a higher current, because when there is a difference in voltage, there will be inrush current supplied from the cell from a higher voltage to a lower voltage, right? So in that case, there will be a lot of power involved, lot of energy involved, which will ultimately affect your capacity. But in passive balancing, since it is always in milliamperes, or let's say in lower amperes, so in that, the current which is being used, which is being transferred or being used or being lost, is very minimal, which will again help you to improve, get the maximum capacity out of your battery pack. So you have to decide based on applications. In places where you are already oversizing the packs, and keeping the delivered capacity lower, you can always prefer active balancing, because that will give you better results. But in places where you have exactly sized the battery pack according to the consumption, and where you do not want the actual capacity delivered to be lesser, and also in applications where C rate, charging discharging rate is lower, so the chances of unbalancing are also very less, or the I would say the significance of unbalancing is very less. You can always go for passive balancing. Now the other thing is thermal management integration. So as you know, like lithium batteries are, can catch fires, have some safety hazards applicable to it. So to have effective thermal management within your battery pack is very necessary. So how BMS helps it? BMS helps it in two ways. Let's say you have a chiller or a cooling unit attached to your battery pack. That chiller or cooling unit can communicate with your battery pack, and the BMS can tell it when to be switched on or when to be off, when the battery needs cooling or when not. This is one way. The other way is the BMS also have some temperature sensors, or I can say thermistors attached to it. So basically, you can place those thermistors onto your battery pack, and then see on the onto your battery packs, and that is basically decided based on the thermal results that you get. Let's say you are keeping your battery pack at 45 degrees Celsius, and then you find, okay, this particular cell in your battery pack is getting the most heated, so that becomes the hotspot of your battery pack. So you can place your thermal temperature sensors over there. But again, you also need to know how many thermal sensors you need, right? So you need to select a IC with a particular temperature sensors you need. Let's say you build up a battery pack where you find there are six hotspot areas. You need to monitor all those six hotspots area. So you need at least six temperature sensors present, so that it can record the temperature and give feedback to the BMS. Then obviously the basic principle, which is safety and fault detection. Whenever your battery pack goes out of range, whether it is in terms of voltage or whether it is in terms of current, the BMS should be able to get the data of those cells, and and isolate your battery pack from the load, so that no unforeseen incidents occur. And then also you have to understand, okay, you want to give a over voltage protection. So over voltage protection, the let's say for electric chemistry, you want to protect your battery pack at 3.65 volt per cell. But for NMC chemistry, you need to select a IC which can protect your battery pack at 4.2 volt. So in these cases, you need to understand what kind of IC you select, where the upper voltage limit and the lower voltage limit is as per what you need within your battery pack. Then comes the communication protocols and integration. As much as the battery packs are becoming smarter and smarter nowadays, and because of the safety hazards that it has, it's very important to actually monitor the battery pack data from time to time to understand how your battery pack is behaving, and that is purely done through communication protocols. So the BMS has a lot of communication protocols. It depends on what you want, what your system wants. Let's say you have a motor controller which can only work on RS-485 communication protocol. So you need to select an IC of the BMS which can support only RS-485, or it has different protocol functions. If you have a requirement for a CAN communication, then you need to select an IC which has a CAN communication integration into it. The other thing is scalability and modularity. As Mr. Ashwani gave an example of the Tesla battery pack, where there are multiple modules connected in series or parallel. So you need to select a BMS or an IC which can support scalability either in series, scalability in parallel, or a mix of both maybe. So accordingly, you need to design the BMS where you want the scale. Let's say if I talk about the three-wheeler battery pack, which is used in commercial or passenger vehicles right now, they don't need scalability because there's a space of fitting only one battery pack and there are only 16 cells in series. Okay, so in that case, you don't need to select a BMS or an IC where you want to scale the battery packs. But in applications like cars, where the battery pack is too big and the construction is in a modular form, you need a BMS which is scalable in nature. You cannot use just one BMS because you are monitoring different modules out of the complete battery pack, and you need the monitoring and safety protection for all the individual modules present in the battery pack. The other thing is functional safety and compliances. So whenever you are exporting the battery pack to US, Europe, or anywhere outside India or even in India, you need to certify to particular standards and guidelines that the government or the authorities of those particular areas have standardized or given. So in that condition, you need to select components. You need to have the performance of the BMS as per what those standards or what those certification recommends. And then other feature is data logging and remote diagnostics. As I told you, like data is very important in BMS. As with data, you will be able to. Let's say you are manufacturing 1,000 battery packs in a month or so. If you don't have a data, you will not be able to realize how your backpack is performing in different terrains. Let's say I have deployed 1,000 battery packs. 200 of them are in negative temperature zones. 500 of them are in plain areas or in normal temperature zones. A couple of them are in rough terrains. So you need to have that data within your hand, at least a 1 month data to analyze. Okay, what is the performance of your battery pack? What factors are affecting the life of your battery pack? What factors are affecting the SOC estimations of your battery pack? You need to analyze and then keep on improving. And then again, because India is a very cost sensitive market, as everyone knows, so we always need to trade off things and build a product which is commercially viable. You cannot keep on adding each and everything on the BMS. You cannot add every protocol, communication protocol. You cannot add every SOC estimation, algorithms. You cannot add every SOH estimation algorithms. You need to select what is necessary for your applications, and based on that, you need to optimize the cost as well. So I'll just show you a typical IC which is used so that you can maybe relate to what is being talked about. So this is a BQ 76952 3C BQ 76952 IC from TI Texas Instruments. Which supports three series to 16 series cells. That means using the same IC, you can design a BMS which has 3 cells connected in series to 16 cells connected in series. Okay, and then the second point, if you see, integrated charge pump for high side NFET protection with optional autonomous recovery. What does this mean? I'll just show you a schematic over here to explain you what actually it means. So if you see the schematic, the MOSFETs over here are connected on the pack positive side, not on the pack negative side. There are two BMS which are made. So one is having these FETs on the pack negative side, and the other one is made with having FETs on the pack positive side. So whenever we have FETs on the pack positive side, that is where we say that it is a high side NFET enabled BMS. How it creates a difference? Because it is easier to get things implemented on the pack minus side of the battery pack because ideally don't have a voltage over there or a potential over there. But when you go to the pack positive side, you obviously have a high voltage or high current voltage over there. Okay, so obviously the BMS which has a high side NFET protection will give you better protections in compared to the low side NFET protections. But again, it will be slightly costlier because the components that you select will have to able to handle a voltage range of that. Let's say you're building a 60-volt battery pack, so the high side NFETs should be able to have that be able to handle that kind of a voltage range. Okay, so when we move down, you can see extensive protection suite, including voltages, temperature, current, and internal diagnostics. So that means that there's a voltage protection enabled. That means you can get protection for upper voltage limit and lower voltage limit. You can get protection for over discharge current, overcharge current. You can get protection for high temperature and low temperature connections with this IC as well. And it has two independent ADCs. That means ADCs means analog to digital converters. So as you know, like when you use a temperature sensor, right? So the values that the NTC record is analog in nature, but the value that the IC understands is digital in nature, right? So you need to have ADCs in place within the BMS so that you are able to get the digital value of the analog value of the voltage and current that is being received, and accordingly you can transmit the data to the to your IC or the PMS. Okay, and as you can see, high accuracy Coulomb counter with again, as we mentioned, what is the SOC estimation technique that is used. So in this particular IC, they are using Coulomb counting, right? Coulomb counting means that they are measuring the SOC by the amount of the current that is traveling through your battery pack. And again, when you say current, so current is something which is obviously related to the voltage drop across voltage drop and resistance between the 2 points. That is how current is calculated. Using the basic Ohm's law, V is equal to IR, where you can have a resistor common, you can have a voltage drop common, and then you can measure the current. So and then again, the cell voltage measurement accuracy, which this particular PMS or IC, which this particular IC has, is 10 millivolt. And this can be used in wide current applications, and these are the basic things which are there. And then this is again an important point: multiple power modes, typical battery pack operating range conditions. So why we need a multiple power mode? Because when the BMS is in active state, it might consume a bit more current, because all the components, all the active and passive components which are present within the BMS will work according to will work and consume a particular amount of current or power, out of which is coming again out of your battery pack. So let's say if your battery pack is in idle state, let's say you are using your car, and you park your car, okay, and there is nothing happening, you're not driving your car. But again, since if the BMS is active, if the BMS is running in normal mode, it will keep on consuming the current, right? So you want, okay, if my battery pack is in idle state for let's say a couple of hours, the BMS should not consume the exact same current, which will again hamper the capacity that you're getting out of the battery pack. So in this particular IC, you can see that they have mentioned as normal mode, which is consuming like let's say 286 microampere. They have multiple sleep mode options. Why multiple sleep mode options? Because you can customize. Okay, let's say if the car is stopped for let's idle for 2 to 3 hours, these components can be off and these components can still keep on working. But if the car is let's say off for let's say 7 hours, 8 hours, it is standing in idle condition, then you can keep it to you can delete more components out of it which does not need to work. And there's a deep sleep mode, and then there's a shutdown mode. Okay, let's say you are traveling for a month, or let's say you're traveling for a month to a different place. Your car is just sitting. Your car is just standing at a particular parking area. It is in idle condition, so there's shutdown mode as well. Which using this mode, the PMS can go into complete shutdown mode, and it will help to save the capacity loss from your battery pack.
Again, for interrupting.
Yeah.
But we are running out of time, so I please make it a little bit concise. I know you are in a flow, so you are sharing a lot of data which is useful for candidates.
Sure. I'll try to finish it up. So again, you can see, I'll just skip this part. So this is a very detailed part of IC. You can go through the Texas website, download a sheet, and then understand what a particular parameter can be. So this is a schematic or an architecture of how the BMS looks like. There's a MCU over here, which is the master control unit, which is the IC that I just showed you. Okay, there's a AFE part. analog front end part, which will have analog to digital converters, ADCs, and communication ports and everything. And then you will have like this particular again. There's a difference in this BMS. So this BMS, if you zoom in and see, this is a low side FET production BMS, right? This is not high side FET production. So you'll have MOSFETs over here for switching and everything. Then you'll have different kind of communication methods or protocols available. And this is how the typical architecture of BMS looks. So again, going back to the PPT. So I just showed you about the IC. I just quickly show you the typical MOSFET data sheet that is used. So this is a MOSFET data sheet that is there. As you can see, VDC 100 volt. So let's say you are making up a BMS for a battery pack which is 60 volt. So you can obviously use this MOSFET because this is VDS 100 volt. It can easily support. RDS on is a very critical parameter in the MOSFET selection because as less, I mean this basically determines what is the heat loss from your MOSFETs, how much your MOSFET will get heated during the operation, right? So this particular value as lower as possible you can select for a let's say you have 10 different MOSFETs, so you can compare which one has the least RDS on, and based on that you can select the MOSFET, so it will dissipate the least amount of energy in the form of losses. And then you have drain current. Then you have drain current, which is again selected on continuous current that is needed from your battery pack, and also upon the short circuit current which is there. So there's a derating curve, and if you go through the data sheet of the MOSFET, you will find a derating curve in which you will see like what is the maximum pulse drain current that your MOSFET can sustain at what temperature. So you can accordingly select your MOSFET, keeping in mind that the short circuit condition will also arise, and in that the current can be 4 or 5 times the value of the your battery pack continuous current requirements. So I'll now quickly go through the last slide, which is there. That is emerging trends in BMS and role of AI. So a lot of things are happening because see, lithium battery, everyone has realized that it is more of a data-driven thing. You cannot actually predict the behavior just on the basis of let's say 100 cycles or 200 cycle. It is a data driven thing and it changes subsequently. Let's say you will have a particular SOH at let's say after 500 cycles, but it is possible that after just 50 cycles more there will be a very significant degradation in the SOH and delivered capacity part. So that all can be achieved when you have data sets available. So the role of AI gets, very important. It's increasing day by day. The role of AI is increasing day by day, and a lot of BMS are now coming with predictive maintenance. They are predicting the behavior of the battery pack based on the performance that the battery pack is giving from day to day, and they are calculating the SOH and calculating all the parameters of the battery pack. They are also sending alerts based on the performance that okay, you need servicing of the battery pack, or there's one cell which is getting which is performing below par as compared to what the expectation of the performance from a particular cell or a battery pack is. So yeah, AI is the next thing that people are working upon, and most important thing which I see from AI is it would be very easy to create a digital twin of the battery pack, because right now when we do the thermal simulations or when we run the thermal simulations of softwares like ANSYS and CAD, so basically there's a very big problem where we take only the initial DCIR which is there, because we don't know like after 500 cycles how much will be the DCIR. So the digital twin that is created on ANSYS using those values, or on any CAE software using those values is not that accurate, because you don't know after 500 or during the end of life of battery pack what will be the performance, right? So having those data sets will make it easier for the engineers to create a digital twin which will actually be able to give you results, give you expected results for the end life of the battery pack as well. So yeah, this is I think this is done from my side. Thank you everyone, thanks for listening. And Keshav, if you are there, can you please start the demonstration process?
Yes, sir. Hello. One more request, Siddharth. If certain voiceover is needed during demonstration, please provide that.
Yeah, sure.
Some explanation or something is required. Yeah.
Keshav, can you please start? Please switch on the video and start the demonstration process.
Yes, sir. This is our BMS. super power 16 has 100 MPa. This is a BMS tester machine. You can see here we connected the harness to our machine from series 1 to 16. Now we connected the pack negative. You can see C minus and P minus to the BMS pack negatives, and area was battery positive, battery negative output one. This one is our 12 volt power supply where we are giving to wake up the BMS. And you can see the parameters what we fetched for the testing. Now we are checking the balance turn on voltage, minus turn on current, overcharge voltage, the overcharge recovery voltage, same like discharging, and the total overall pack voltage protection and recovery, and same in the total pack for under voltage and under voltage recovery. In the discharging over current protection, we are also cross checking, and charge over current protection. This is the sample of the OK BMS. Now we can again, I'm going to again start the testing from here. You can see, start testing.
Keshav, can you please zoom in a bit?
Yes, sir.
थोड़ा zoom कर लो please, मतलब मोबाइल की स्क्रीन को थोड़ा पास ले जाइए कैमरा.
Yes, sir. Now I think let's see. This is accurate testing.
So, Siddharth, can you shed some light on why testing is needed for the BMS and what exactly is being done here? Why do we need this kind of testing equipment at all?
Yeah, so it's very important. So right now the scenario is where a lot of majority of the BMS are being imported from China. There are a couple of Indian vendors as well who are developing it. But when you get the BMS, there are tolerances in BMS. There are tolerances in IC as well, right? So and also you need to protect your battery pack at a particular voltage limit. Like you need to protect your battery pack at 3.65 volt and 2.5 volt. Let's say your BMS vendor so it says, okay, this is I've given that, I've protected your battery pack at 3.65 volt. But how do you identify whether it is cutting off at 3.65 volt or whether it is cutting off at 2.5 volt? Or also at the current level, let's say there's a over discharge current, because these things are very critical in a battery pack. Let's say if the BMS is not able to cut at 3.65 volt, then there's a chances of fire as well. So you need to identify, and there are 16 strings. Again, as Keshav told, this BMS is for 16 cells in series. So there might be possibility like, okay, let's say 10 strings are okay, they are cutting off at 3.65 volt, but the remaining 5 strings are not cutting at 3.65 volt, which can create imbalance for your battery pack as well, and can also create, safety issues going forward. So these parameters are very important to check in-house when you receive the BMS in lots, and 100% testing of BMS is required. Keshav, can you now show the assembly of BMS in the battery pack?
Yes, sir.
Can you explain, please?
Yes, sir.
I think Keshav is holding the camera, or someone else is there who is holding the camera?
Keshav, can you ask someone else to hold the camera so that you can easily
Hold the
explain?
camera, stable, yeah, that will be helpful.
See, this is our back positive. This is going in the back side. So now you can see this is our back positive. This is going in the BMS battery positive side, and this is our pack negative. This is going in the battery BMS negative side. And the same side you can see we are taking
BMS wait, output positive. So the from below side, this one is our output positive wire. You can see that one is clearly from there we are taking, and from the output negative we are taking in our MCV from the BMS we are taking in the MCV. You can see this wire, which is coming from the BMS output negative, and from MCV we are taking it out from the main negative from the output, and same as for the positive. You can see from the BMS positive wire, and this is our sensing part, which is started from the main negative. You can see it from there, same as for the 16s from the B0 to B16s.
Can you also show the LCD screen and switch that is present?
Yeah, yes, sir, of course. You can see this one is our LCD display. Oh, wait. Sir, this pack are currently yeah, this pack is ready. Firmware uploaded. And this one is our display, sir. There is the pack over voltage, current, SOC, and warning, which is showing N means no warning is there. And this is our switch. We can see other parameter also. Cells, temperature, warning, capacity.
Yeah, that is all, Keshav. Thank you.
Thank you so much.
You can switch on. Yeah. Hello.
Yeah. So thank you very much,
Yeah,
Ashwani and Siddharth, for
actually
that.
demonstrating these things in online manner is a little bit tricky and difficult.
It's very
You
hard.
can see in a factory layout thing, but yes, we wanted to give certain snapshot, like how BMSs are tested and how integration takes place. So whatever you saw in the video, it had 16 cell battery bank, and I think Siddharth already explained the ICs and BMS with 16 cells connected in series. So those battery bank, what you saw, those are being manufactured for stationary storage application with around 38 volt and maybe 100 Ah capacity, right? So that's how people in a small scale manufacturing unit manufacture these battery banks. The core issue, people small scale manufacturer is related to BMS integration. Okay, so a lot of scope is there in those integration, validation, and all. Yeah, yeah, Tanjeev, over to you.
Great. So before we go into the Q&A from EV Acad, I would like to talk about our programs that we have. So since Ashwani had said in the beginning that this is a very short time to go deeper into the subject. Okay. So to know more about BMS, to learn more about it, you need to spend some time and effort. And for that, we have our programs and Antariksh is Arun here.
No, sir, he's not here.
Great. Fine. What I'll do is I'll just have a quick run through our programs. We have a total of three programs right now with IIT Bhubaneswar REP. Okay, the first one is proper 9 month certification program, followed by which we have a smaller duration program that is a 6 month and a 3 month program. Okay, So you can go through our website on evacad.com. I have posted the link. Yeah. So please go through these programs, the details of the programs. It is very interesting to know more about the EV domain, where you get to learn more about the skills that are actually required in the industry right now. Just a second, I'm sharing my screen. So with IIT Bhubaneswar, REP and EV Acad, we have a couple of total three programs right now. So that is a certificate in EV model-based engineering, advanced certificate in e-powertrain and batteries, and a PG certificate in e-drives and battery systems. So basically, whether you are a student currently in the third year or the final year, you can go for the shorter duration of about 4 months. Uh, if you have a little bit of work experience, you have more time, you have more space to go deeper into the e-mobility domain, you can go for either the advanced certificate in e-powertrain and batteries or take up the PG certificate in e-drives and battery systems. Okay. So you get to learn from the IIT faculty, the industry experts who are well versed in the EV, in the e-mobility domain. Then all our programs are practical based, so you get a lot of real world knowledge directly. And there is a lot of immersion sessions also that goes in these programs. Okay, so you are free to opt for additional the immersion sessions as well, and go deeper into the subject. So how do you enroll yourself? So you go to the link that I have posted. Okay, you show your interest by clicking on the apply now button. Okay, fill up your details. Our learning consultants will contact you. You can have your doubts cleared. Okay, then if you are willing to go ahead, then we have a screening session for you where you'll be reviewed about your interest, your statement of purpose that is there to do these programs, and then you book your seat by paying an admission fee and then start your journey. Okay. So who this program is for anyone from an engineering or a science background. Okay, and if you are be a student, graduate, fresh graduate, you are working professional, anyone working in the automotive, mechanical, or electrical disciplines. Okay, or if you want to start your own business. Okay. So you are open to do this program. Okay, and we welcome you all to join in and start a journey in the e-mobility domain. So let's go on to a few Q&A questions that I have posted. We have one question. I guess to Mr. Siddharth, you can answer. Please explain how do the battery pack calculation for particular power level and backup time. For example, load is 1 kilowatt and backup time is 20 minutes, voltage is 24 volts. Someone wants to know about the calculation.
Yes, so it's very easy. Just need to understand like what is the current required when you're running a 24-volt load. So let's say for a one kilowatt and 24 volt, the capacity, the current that will be running through the if you're running it for 1 hour, will be 1 kilowatt divided by 24 volt. You will get a current, and that if that you can assume. Let's say you are getting. Let's say I'll do the calculation one minute. So at let's say one kilowatt, you are getting around 41 ampere of current at 1 kilowatt. So if you run it for 1 hour, so the battery pack capacity will 41 Ah that will be required. So if you half it down, like you have to then convert it for 20 minutes. So if you half it down, so let's say 0.2, just a second, 0.33. So it will be coming around 13 AH. So it's very 14 AH actually, approximately equal to 14 AH. So first you need to divide the power by the voltage to get the current, and then you have to assume that okay, for 1 hour, if I'm running the that system for 1 hour, so the actual capacity required will be the same as the current. So let's say I'm getting 41 ampere current, so I'll need a 41 AH battery pack if I run the system for 1 hour. Now, if I run it for 20 minutes, you just have to multiply that particular capacity by 20 by 60, get 0.33, and then you will get around 14 H. So the actual system that you need to propose to the customer is around 24 volt and 14 H.
Great. I hope that clears up the query. Then there's another question. Someone wants to know your views on the restrictions being put by our government for import of BMS from China.
See, the government has placed restriction, especially in the EV applications for L category vehicles, whereas they are, asking the battery manufacturers or the vehicle manufacturers to use components apart from cells. Only all the components should be made in India. But the problem is when you see the BMS, there are a lot of semiconductor components involved. Okay, for which India is still not ready. Okay, so I need government should first focus on how to get that particular ecosystem where semiconductor components like MOSFET, ICs, diodes should be manufactured in India, and thereafter if they impose those import restriction, then India can be fully independent in that way, and India can be very confident with supplying the customers with all the components. But if we do not have an ecosystem for semiconductor components, it's very difficult because ultimately we will have to be dependent either on Korea or Japan or China for getting those components like MOSFET and IC, and again India will only be doing assembly. So that does not make any difference. Again, the cost will be higher for those parts, which will again increase the cost of the complete battery pack or the electric vehicle. So I think the focus should be towards developing the ecosystem for the semiconductor components, and once it is developed, yeah, surely they can have import restrictions on the BMS.
Great. Thank you for that. There's another question. Is there a trend towards having universal BMS platforms for different EV types?
Can you please repeat?
Is there a trend towards a universal BMS platform for different EV types?
No, I think there is no universal platform as of now. I mean, every company that is manufacturing their vehicles or BMS have their own developed platform. Obviously, the algorithms and the method of calculations can be standard, but the platforms are all different. They have their own platforms. They have their own features of those platforms. Some can, show the all the cells data. Some don't want to show the cell data. Some want to show the total capacity, cumulative energy that is going in and out of the battery pack. Some don't show it. So there's no universal platform as of now. Everyone have their own customized way of showing the data on what they want to show to the customers.
Great. So someone had raised their hand. Vishwasai, do you have any query? You can post it on the chat because we don't have a.
Vishwasai has already posted what will be the real-time issue in a manufacturing unit in the BMS line.
Okay. So the major issue that I observe over here is there are two major issues basically. One is during the connections of voltage wire, voltage sensing wire harness, because if you let's say connect the third sensing, third series voltage sensing wire to let's say to a fifth series or sixth series, then your resistors which are there for the balancing, passive balancing, bleed resistors tend to get burned. Okay, so this is a very critical issue which is always there. The second thing is during the integration time, when you are integrating your BMS with the inverter or motor controller or charger, there are a lot of issues during the interfacing. You need to have the complete hold on the communication protocol that is present. So that is another issue while you are, manufacturing the battery pack using that particular BMS.
Okay.
Brijesh, can you unmute yourself and say your question? I did not get your question. Is any calibration or validation needed after car maintenance? What do you mean by that?
I don't think there is option to unmute.
Brijesh,
I think, Ashwini, I think he mentioned about calibration and validation of the BMS if it is needed after the car maintenance.
after service, after service.
Yeah.
Yeah, then it's a part of service itself. They do analyze the data. They have a specific OEM given module through which they can do a lot of data analysis and all. They simply plug in inside the vehicle, and they can plug in inside the BMS as well. Sanjeev, Arun has a very specific question to you. I am a freelance electronics product designer. After learning BMS, what are the scopes that I have?
Sorry, that was not audible. Can you just repeat? I
It's
didn't.
there in the question answer queue, Arun A.
I am not able to see that. Maybe it was directed to you.
Okay. So he is asking about I am a freelance electronics product designer. After learning BMS, what are the scopes that I have?
Okay. See, there are a lot of career opportunities in the industry. Let me just share. Let's see. Now, basically, across the globe, there is a lot of growth in the e-mobility domain itself. Okay, and batteries being the hearts or the brains of the EVs, there is a lot of opportunity. Okay, going through the BMS, you can either go into like we have Sella Power Tech, or you can start your own business. Okay, or you become a BMS engineer. Okay, you go deeper into the subject, or you can start your research as well. Yeah. So you have all the opportunities, all these options to go through. So once you have gone through the courses.
So I will rephrase this question for Siddharth because you are in a similar field. So how do you see your competition? Is there any scope for your competitors in the industry?
Well, I have tried not to create any competition so far, but yes, I mean, see, going down the line, as the country is moving towards indigenizing each and every component that goes into the battery pack, there is obviously scope of having more, consultants or I could say design houses or project developers in India, because I don't see a lot of battery specific consulting companies or design houses which are focused. I see a couple of companies like TCS, Cognizant, Deloitte offer services like thermal simulations to clients like Mercedes, but I've seen those simulations like those are below par. I mean, to be very frank, they're very below par. They're not actually based on actual conditions. They're just static simulations. Okay, so going down the line, when everything is being indigenized in India, there'll be a lot of scope of having design houses, or for BMS as well, for the battery pack as well, and for the components as well.
Did anyone has any other queries? Or if not, then we are ready to conclude.
I think one person, yeah, Vishwa Sai has asked a very good question, which is why CAN communication is used in automobile industry instead of UART and SPI. So, Vishwa, it's a very good question. So, basically, when you see an electric vehicle, there are a lot of components involved, right? You have motors, you have sensors, you have switch gears, and everything. So having a lot of these components, create noises. I mean, if you understand electronics, there's a very important factor like noise during the signaling process, right? So I2C and UART are a way of communication which are not noise tolerant, but can be a noise tolerant method of communication, and also using the CAN communication on the same communication line, you can transfer data from the motor controller, from the BMS, from the chillers, from everything on the same communication line. Different buses can be attached. Different components can be attached. Whereas in I2C has multiple, but UART is basically point to point communication, right? So surprising. So I2C and UART are used within the BMS. Let's say if the MCU has to transfer the data or get the data from the sensors, then it will get transmitted through UART or I2C. But since because the communication is happening from point to point, okay, there is no other things, other components involved. But when you are integrating or communicating your BMS with other components, there are like multiple components involved, in which CAN communication is better. It is a long distance communication, and it can on the same communication line, it can connect through various nodes, multiple nodes, which is not possible in case of UART. uh, yeah, so that is basically a couple of reasons why people prefer CAN communication.
Okay, did we cover all the questions? Yes, yes. How much time it would take to convert to IC engine to electric? How much time it would take to convert to IC engine? I guess he's asking like 100% conversion from IC engines to electric vehicles. By
We
which
cannot tell. I think the government can tell.
So mixed answers will be there. So the plan is by 2030, the plan is to have 30% conversion into different segments, so like two wheeler, three wheeler, and all. So maybe you can refer to certain government policy documents. I personally see maybe beyond 2040 or so. So 100% conversion, I do not see. Like I'm not very positive for a 100% conversion by before 2040. But yes, in certain segments such as two wheeler and three wheeler, it might come early as well. Like by 2030, we may see overall conversion of two wheeler and three wheeler vehicles which are being run on petrol and diesels. Okay, but passenger cars, passenger buses and heavy duty trucks will take their own time.
Yes, another question, Vishwasai. As you mentioned about shutdown mode, then what about limp mode? Is it important?
I think
Can
these
you
are very
please elaborate
specific
what is?
questions. Uh, Siddharth has already. Mr. Tanjeev, would you be sharing email IDs of panelists with the attendees so they can direct directly their these kind of questions, specific questions to experts?
Yes, yes, sure. We'll share that. Okay. So thank you, Ashwani Pandey and Siddharth Advani for sharing your expertise and experiences with us today. We had a we appreciate the engaging questions from our participants as well, and the insightful responses from you both speakers. So, if you found this session valuable, consider exploring EVA CAD certification programs to further enhance your skills and career in the EV industry. Okay, I hope you become a part of the e-mobility domain because there's a revolution that's going on, and it's good to get onto the bandwagon as early as possible. Okay. So with this, I say thank you to each and every participant and to our both our speakers. Thank you for participating and such an insightful masterclass that we had today. Thank you and have a great evening ahead.
Thank you, Tanjeev, and thank you everyone.